Hello, I'm Alex Gonzalez and this is my Lab 5. So this lab's main purpose was to see what happens when you drop a magnet down a tube of aluminum foil. And then a lot of this lab was coding, so we are going to code an experimental model or a computational model just to compare the two and see how accurate our experiment was. Some physics principles that we ended up using in this lab were Faraday's law, the Biot-Savart law, and Newton's second and third laws of motion. We're going to be using each one with each other, so comparing gravity's effect on a magnet to what the tube and the magnet falling through the tube changes that. So in this procedure, as you can see in the right graphic, we're going to film ourselves dropping the magnet through the aluminum foil tube, and then we're using that film to actually time it, since it's going to be more accurate than if we were to do a hand timer. You can see in the video I drop it through, and it takes quite a bit longer than when you just normally drop it for it to come out the other side. Some points of error that I found though were the magnet. I looked above for some of them, and it was sticking to the side, and my tube of aluminum foil seemed to have some factory defects, so there was some ridges on the inside that it was getting caught on several times, and that could have affected the times I was getting. And also, as you can see, I didn't notice this until actually getting the time. My thumb was blocking how you can see the magnet, so this could have caused some additional timing issues that I would change if I were to do this experiment again. So here's the data that we found throughout the lab. The average time of the magnet falling through was 2.776 seconds. I decided to calculate how fast or how much time it would take the magnet to fall not through the tube by using the equation displacement equals the initial velocity times time plus 1/2 acceleration times squared, using 9.81 meters per second squared as the acceleration and the displacement as 0.306 meters, since that was my length of the tube. And by doing all that and solving for t, I found that it would be 0.25 seconds if it wasn't going through the tube, which is a pretty significant difference between the two. So in my code, I just showed a few parts here. This was the function that we used in the previous lab to find the magnetic field of the magnet. And underneath it is a new function that finds the magnetic flux. And you can see part of it, distance and speed, play a big part in it. And this all comes together with our initial values found in the lab to show this computational model. And I couldn't get a video of it going through, but the time it gave me was 3.338 seconds, which is about 0.562 seconds off my experimental value. And the last part of this lab was solving or answering these what if questions. So for the first one, it asked, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So I started off using the V equals IR formula, and I said that with a lowered resistivity, R is going to be lower, leading to a higher I. And this higher I leads to a larger attraction between the magnet and the tube, meaning the magnet could, it's going to slow down significantly and could even be suspended in midair by the tube. And the final question asks, what if holes or slots were cut in the tube? How would this affect the ring currents in your model? So I said, similarly to the first one, decreasing the area, you'll actually be decreasing the current. And as we saw in that previous problem, a decreasing current will make the magnet fall faster, and it'll act as if the tube wasn't there, or it was a much smaller tube.